Hi all, welcome back and good evening to the third week of TA live sessions for AI knowledge representation and reasoning. First of all, can all of you hear me clearly and is the screen visible?
Yes, it's visible.
Okay, thanks for confirming. So, yeah, without any further delays, we can get started. So, today we'll be discussing some questions related to the week 3 content of the course, which dealt mostly with propositional logic or PL. So, yeah, let's get started. So, this is the first question in front of you. So, this question says that let the set of atomic sentences in propositional logic or PL be P, Q, R, and S. And we have to choose among the four options given which of the following sentences, which of the following are sentences of propositional logic. Okay. So, which of these options do you think form sentences? So, recall the definition of sentences from the video lecture and remember how it related to a well formed formula. Okay, and see which of these are making sense in terms of the connectives that have been placed in the options and the placing of the parentheses or the brackets in the options. Okay, there's one option, there's one vote for option B, but make a note of the parenthesis before the and operator in option B. That doesn't make sense, right? uh, a binary operator should be placed between uh, two symbols, right? That's right. So I think most of you get it. So the correct answer is option A, and that is because um, this is well formed. So we have a P and Q. Okay, this is one part of the sentence. Then there is an implication, and then there is another symbol which is R. Okay, and all this together forms a sentence or a well formed formula. The problem with the other options is that here there is a parenthesis just before the and operator, which is not uh, making sense, which is not well formed. Here we have two binary operators placed immediately one after another, which is also not making sense. And in the third option or the last option, we have this unary operator placed between two symbols. This should have been a binary operator, right? So this is again not a well formed formula and hence not a sentence. So I hope this was clear. This was pretty straightforward. Yeah. Any doubts
Sir,
there?
sir, why atomic? The word is coming. It can be directly a sentence in propositional logic also is possible. No?
Yeah. So basically, we are being told that P, Q, R, and S are atomic, so that we don't have to worry about P itself having some sorts of irregularities in its formation. If P was
Okay, sir,
not
right.
atomic, let's say P itself was A and B, right? Then you would have to worry about whether the and has been placed correctly between A and B, right? That's why just for our for making the question simpler, we mentioned that P, Q, R, and S are atomic. Does that help?
Sir, yes. Thank you,
Okay.
sir.
Okay, then I hope this question was clear. If not, please let me know. We can discuss it again. For the time being, let's move on to the next question. So this question gives us a knowledge base. Okay, uh, this is a knowledge base given to us, and there are different facts given inside the knowledge base. These are the different facts: P or not R, R and T, W implies S, P and S together imply Q, and T implies not of S. These are the different facts given to us, and we have to deduce which of the following facts can be deduced or derived based on the knowledge base and the traditional rules of inference that we have seen till now, that is modus ponens, modus tollens, and so on and so forth. Okay, so maybe I'll give you a couple of minutes. You can, if you have a pen and paper around, you can try to work it out yourself, and then we'll have a look at the solution. Okay, any partial solutions till now? Okay, if not, that's fine. Let's try to work it out together. Okay, so I have this knowledge base written over here. Okay, and let's try to derive different facts based on whatever we are given. Okay, so the first thing that is given to us is P or not R. If we just reverse the symbols, we can rewrite it as not R or P. It's the same thing, right? And this can be written as R implies P. Are you with me till this point? So
Yes, I'm with you.
okay, that's great. So just to address a query in the chat box, basically what we did over here is that just we swapped the two the things that the symbols that were on the two sides of the or operator. Okay, a or b is equivalent to b or a, right? That's what we just do over here. P or not r can be written as not r or p, and this can be written as r implies p. Okay, not r or p is equivalent as r implies p. Now that we have R implies P from this particular fact, R and T, we can infer both R as well as T, right? That is, for R and T to be true, R has to be true and T has to be true. Now combining R implies P and R, we can derive P, right? By which rule? Can anyone tell me the rule?
Modus ponens.
That's right.
Modus ponens.
That's right. So we use modus ponens to derive P. Now similarly we have T over here, and T implies not S. So we use that to derive not S. Right? Now we have not S and we have W implies S. So when we use both these, can we use modus tollens to imply something or derive something? See, we have W implies S and we have not of S.
Not W.
That's right. We can derive not W using modus tollens. Okay. And is there anything else that we can derive? No, right? I don't think so. We can derive anything else in this knowledge base. So these are the three facts that we were able to derive, and let's mark those particular facts in our answers. Okay, so we were able to derive P, right? We were able to derive naught of S, and we were able to derive naught of W. So let's check our answers, and that is what we have. We derived P, not S, and not W, and S, W, and not of P we were not able to derive. Okay, so I'll just leave this on over here for maybe half a minute or so, and you can convince yourselves that we went through a thorough derivation, and then we'll move on to the next question.
Ritvik,
Yeah.
with respect to the formula where we have P and S implies Q, why did we use the derive against that and to try to derive something else?
Okay, Varun, your voice was breaking slightly, but I'll maybe just repeat the question you said, and correct me if I'm wrong. So you were saying that why don't we use this particular fact to derive something, right?
Yeah, along with the P value which we derived earlier.
That's right. Okay. So, in order for us to be able to apply this particular rule, we need P and S to be true, right? Now, we know that P is true based on our derivation, but we have not been able to derive whether S is true, right? We are able to derive that not of S is true, but we were not able to derive whether S is true. Because of that, we cannot say that P and S is true, and because we cannot say P and S is true, we cannot imply Q. So we are not able to use this formula in our derivation. Does that make sense, Varun?
I mean, I don't know what's the truth value of that, but can't we assume in that case that
No,
it
no,
is
we
true?
can't assume. We can start with only one assumption, and that is whatever is given in the knowledge base, that is true. Okay, so the facts given in the knowledge base are true, and the rules given in the knowledge base are true. Okay, so we know that if we had P and S together to be true, then we could imply Q. But since we only know that P is true based on our derivations, we cannot say for sure whether P and S together will be true. Okay, that's why we are not able to use this rule. The only assumption that we are going to begin with is the facts given in the knowledge base are true, because that's the definition of the knowledge base, that anything that is included in the knowledge base should be true. Does that help, Varun?
Yeah, that's good.
Sir, the same problem.
Yeah.
Sir, the same thing is possible to solve by using tablax method. Maybe it is there in this week or next week.
Yeah, yeah, it's in this week itself. It's possible to solve it using
We
the tabular method as well. That's right. So there we
can you make just at least the minus s e point? Is it possible to make it e
like
my not s is how to
not of
prove
s.
or how to
Um,
initiate this? How to initiate this
so
solution by
basically,
using
in tabular
tablax?
method, the way you do, let's say you have two simple things given in a tabular. Okay, one is a and b. I'm talking about a hypothetical other knowledge base. Okay, I'll come to this knowledge base a bit later. Then you have p or q.
So my question is,
Mm-hmm.
if we want to prove only A, whether P true or not, then it is possible to prove easily by using tablax. If
Yes.
we have A to F, six are their options, then every option I have to negate it and we have to go further, is it?
That's right. So tabular method is mostly used to check whether a particular model is satisfiable or unsatisfiable, or whether it is a tautology or not. So it's not ideal if we apply it for every option again and again. But in that case,
Oh,
I mean, basically depends on your comfort level. If you feel more comfortable with the derivation procedure of a tabular method, you can go ahead with that. For some people, it might be more efficient to use a tabular method. I personally prefer this graph method, where we have all the facts listed. We use these, edges to arrive at new facts,
sir.
and then proceed like a tree, basically. But it's completely up to your comfort level. any method that you feel would be faster for you and more efficient for you, you can rely on that.
Okay. Now in this question, is it possible for you to now tell for minus not yes? Is it okay now to tell?
We can try that, but let's keep that for maybe towards the end of the session, so that we first discuss all the questions
Okay,
and
sure,
then come
sir.
back to this.
Sir,
Remind me if I
right,
forget about this, okay?
right. Thank you. Yes, sir. Thank you.
Okay. Okay, then let's move on to the third question. So the third question is also very same. Again, we are given another knowledge base. It's not the same knowledge base at the last time, but it's a different knowledge base. And we again have to follow the same level or same process of derivations and arrive at some facts. And then we have to decide which of these options can actually be derived given this knowledge base. Okay, so again, I'll leave it on here for a couple of minutes, and then you can attempt the solution, and then we can discuss the solution.
P. Derive P.
Okay, so we have one vote for P. What about the other options? Let's try and derive some things. Uh, yeah, is there a question? Okay, maybe that was by mistake. No worries. Let's try to approach it step by step and see if we can arrive at some facts. Okay. So again here, let's look at the first fact given to us, which is P or not of S. Again, we can rewrite this as not of S or P, right? And this can be written as S implies P. Okay. Now, based on this particular fact given to us, we know that S and W is true. So S has to be true and W has to be true, right? And yeah, is there a question?
Sorry, another one is not P.
Not P. Okay, that's great. Yeah, let's see how we derive not P. So first we use this one, S implies P and S, to derive P using modus ponens, like one of your friends said. Then we have W and we have W implies not of P. So we use both these to derive,
Modus ponens.
yes, modus ponens against, to derive not of P. Now, one thing that you might be thinking, wait, we just derived P and we also derived not of P. Does that lead to a contradiction? Well, it does lead to a contradiction, but as of now, we are focused only on the things that we can derive. Okay? If after the whole derivation is complete, we have contradictions remaining in the set of facts that we have derived, that is a thing that we will worry about post derivation or after the derivation has completed. Okay, that will lead us to infer whether the model is satisfiable or unsatisfiable, or so on and so forth. if we had used a tabular method instead. But yeah, for now let's focus only on deriving facts that can be derived and focus on the contradictions later on. Okay, anyway, so now we have derived p, s, w and not of p. Okay, now we have p to be true and we have s is also true. So using p and s together,
P conjunction S.
yes, we can say that p and s is true.
P
And using
conjunction.
p and s and this rule, again using modus ponens, we can say that q is true. Yes.
Yes.
Is it possible for us to derive anything else? Are we forgetting something? Using the facts that we have derived till now, can we use modus tollens anywhere? So focus on this particular implication and this fact. Using these two, can we derive something?
Yes, negation, not S.
That's right. We can derive not of s. Again, another contradiction that we come across. Not of s as well as s. Right? Is there something else that we can derive? Again, using modus tollens.
Yes, not S.
Focus on this particular fact given to us and this particular fact.
Which one?
So
P and
p and w implies not of p. Using these two, can we derive something?
not W. Yes.
Yes, we can derive that because p is essentially not of p, right? P is equivalent to not of p, right? So we can use modus tollens again over here and derive not of w. Another contradiction, not of w and w are both present in our derivation. But is there anything else left for us to derive? I don't think so. I think we have derived everything. We have derived p, we have derived s, we have derived q, not of p, not of s, and not of w. And I think that covers all the options given to us. So, in fact, we can derive all of these options given this particular knowledge base. Okay.
Yes.
Again, I'll leave this on here for maybe a minute or so you can convince yourselves that we derived everything. And then we can move on to the next question, which is based on tabular method. Okay, so any doubts there in this question? Okay, if not, then that's great. Let's move on to the next question then. That's based on tabular methods and some concepts that we need to understand the tabular method. And so the reason I was waiting for these questions is so that once we have the tabular method concept slightly more resolved and practiced, we can go back to the question that Khalid had asked, whether we can derive naught of s using the tabular method in the first knowledge base that was given to us. Okay. So first thing that we need to understand is what is a model. So this question asks, a model for a set of statements S in propositional logic is which of the following? So what do you think will be the answer based on the lecture videos and the lecture slides that you might have come across in this week?
Answer is C.
Okay, so we have one vote for option C, which is actually correct. So a model for a set of statements is a valuation of the for the atomic propositions that makes all the sentences in S to be true. Okay, what we mean by that is, let's consider a very simple set of statements given to us. Okay, or we don't even need to consider any specific set of statements. Let's say we have some knowledge base. Okay, we have some knowledge base. This has a certain set of statements. Okay, and this set can be represented by S. Okay, this contains statement 1, statement 2, and so on and so forth. Okay, now each of these statements are in turn made up of different atomic propositions, right? For example, let's say P, Q, R, and S are the atomic propositions given to us. So S1 would be made up of P, Q, R, and S, or some subset of those. For example, S1 represents P and Q, right? Similarly, there will be other set of statements as well. Now each of these will have some value, right? Some truth value. So a model is basically one particular set of assignment of values to these propositional symbols, or this atomic propositional basically these symbols in the propositional logic that make the whole set of statements S to be true. Yeah, that is what is given to us in this option. A model for a set of statements S is a valuation for the atomic propositions that makes all the sentences in S true. Okay, so for example, let's say we have only two statements in this knowledge base, P and Q and P or Q. Okay, and let's say a particular valuation of P and Q is P is true and Q is true. If that is the case, P and Q is true, P or Q is true, right? All the statements in the knowledge base, or the set of statements represented by S, are true in this valuation. So we can say that this is a model for the set of statements S. If let's say this was false, then this would be false. This would still remain true, but the total set of statements would not all be true, right? So we can't say that this is a model, right? And a model is something that we need to understand the tabular method. Why is that? Let's look at that. So what happens in a tabular method is essentially, so let's say you have a knowledge base. Okay, you write down your statements in the knowledge base one after the other. Okay, let's say you have, or let me stick with the symbols I was using initially. Let's say we write P or Q and P and Q. Okay, so you write down whatever is given to you in the knowledge base. Okay, then we expand this. Okay, if we can expand it in different ways. If it's an and, if we are expanding a particular statement with an and connective, we are going to expand it linearly. For example, if we are going to expand P and Q, we will add P and Q in the same line. Okay, and if we have P or, if we are going to expand P or Q, we will expand it in branches. So not here, we will write sorry, P or Q can be written as two branches, P or Q. Okay, and we will continue this particular set of derivations until and unless no more derivations can be made. If any of these branches, so depending on how many or statements are there in our knowledge base, or even if there are no or statements in our knowledge base, we will end up with a certain number of branches, right? And we will have to now check whether there is a contradiction in each of those branches. For example, let's say we also had a statement not P in the knowledge base. Then let me use a different color. This particular branch, okay, where we have not P, P, Q and P, this would have a contradiction because of not P and P, right? Whenever you have a contradiction, you can say that this is unsatisfiable. Okay, and when you have all the branches that have no contradictions, then you can say that it is satisfiable, or consequently a tautology. Okay, so that is essentially what the tabular method is. Now when we have to prove a particular statement, what we do is we add the negation of that to our knowledge base and perform the tabular method procedure. So if we go back to the knowledge base that we discussed in the starting, and coming back to Khalid's question, where whether we can derive the not s, yeah, this was it, right? So what we will do is we will add the negation of the statement that we want to prove to our knowledge base. Okay, so I'm not writing down all the facts linearly, but assume that they are written, and then we, in addition to that, we also add not of s, which is equivalent to s. So we add s to our knowledge base. Okay, and then we see whether this addition of this particular s leads to any contradiction with respect to this particular symbol. Now we know that we were able to derive not of s, right, using some rules. We first derived t from r and t, then we used t implies not s to derive not s. Now because of this not s and this s that we added to our knowledge base, there will be a contradiction in one of the branches, right? Because there is a contradiction, we can say that the model where we added not of s to the knowledge base is unsatisfiable. Because that model is unsatisfiable, the opposite of that model, which contains s itself, not of s, that will be true, and hence not of s is there in the knowledge base. I know it might have sounded very confusing, but just think through it, and things shall start to get clearer. Khalid, does that address your query that you were asking?
Okay, it is yes, sir. But I have other things also to prove in remaining 5. So tablex method is taking lot more time than the branch method.
Yeah, so that's what I also feel. Then you have to do, for all the options, you have to do it every time. You have to add a negation of that and then add it to your knowledge base and proceed with the tabular method.
Sir, yes, sir, it's right. Done, sir. Thank you.
Okay, so I personally prefer this branching method that I just showed initially. But if anyone is comfortable with the tabular method, feel free to use that.
Now it is better, sir, even for me. The branching method is also, I feel now I am able to understand after your discussion.
Okay, that's great then. So yeah, either way you should arrive at the same answer. So it's you can feel free to use any method. But yeah, so that was the explanation from my part, and let's get back to the questions that we have. So based on whatever we discussed on tabular method, we'll have some further more conceptual questions. These are not recall based questions, but rather conceptual questions based on our understanding of the tabular method. Okay, so question 5 asks us, eliminating a connective from a sentence in a tabular, which of the following do you think would happen if we eliminate a connective from a sentence in a tabular? Basically, when you say eliminate a connective, we mean to say that we expand a particular statement, be it either connected by and or. So again, recall that there are two cases. We could either do a expansion when there is an and operator, or we could do an expansion when there is an or operator. When we do an expansion with an or operator, there will be branching into two different branches. When we do an expansion with an and operator, there will be extension in the same branch that we were moving forward, so linear extension. So that's right. So Sridhar says that option C and D are correct, and that is in fact true. The reason why A and B are not correct is because we cannot say that there will always be extension linearly, or there will always be extension in terms of branches, right? Depending on what kind of facts we are given in the knowledge base, there can be several different types of expansions or elimination of connectives. So this would sometimes lead to further branching and sometimes lead to linear extension.
So simultaneously, both C and D, how it can be connected? Either C should be right, or sometimes it is D is right.
No. So the question doesn't ask us about simultaneous occurrence. It just asks which of these are possible.
Okay, eliminating a connective.
Yeah, eliminating basically
Both
means.
are possible.
Yeah.
Both are possible. Maybe sometimes C or sometimes D.
Yeah, that's right. Actually, if you think about it, the only reason we are not considering A and B is because of this word always, right? If this word always was not here, even this could happen, result in extending each branch below the sentence linearly. Suppose we have a knowledge base that is filled up with only and connected operators, right? So that expansion will happen only linearly. There will be no branching at all. Similarly, if we have a knowledge base that is composed of only or connected statements, right? Then there will always be further branching. There will not be any linear extension, right? But just because we have this always written in this particular two options A and B, these two options become wrong, because we cannot say that always happens. So linear expansion, Varun, is when we basically add in the same branch. For example, if we have A and B in the knowledge base, and we want to extend it in this particular direction, we write A and we write B, which is basically we are expanding this A and B, right? We are eliminating the connective, and with whatever we are left with after elimination of the connective, the facts we are adding to a knowledge base in the same branch. If we had OR connective, we would have expanded it in two different branches, not the straight ahead branch. Okay. So this is what is meant by this is linear expansion, this is branching.
Got it. Yep, thanks.
Okay. Okay, then I hope this was clear. Let's move on to the sixth question then. So this question tells us, in the tabular method applied to a given knowledge base, so this essentially deals with when can we call something satisfiable and unsatisfiable, and when can we call something tautology. So go through the options, and which of the following do you think is possible in the tabular method when we apply it to a knowledge base? Okay, so Sridhar says that A, D and E. Um, okay, let's look at the options one by one. So the first option says that at least one branch should be a model for the knowledge base to be satisfiable. Okay, so satisfiability basically means that there is some particular assignment of the atomic variables that leads to the whole model having the truth value true. Okay, there might be other assignments or other valuations that lead to the whole thing being false, but if we have even one of them that leads one particular valuation or one particular assignment that leads to the model being true, we will say that the model is satisfiable. Okay, if we have all the particular valuations leading to the truth value true, right, then we will say that it is a tautology, which basically means that it is always true. Okay, and if we have that all the branches are closed, or which closed means that all the branches have some contradiction, so whenever we come across a contradiction in tabular method, we will close that branch, we will not expand it any further, because it's futile to expand a branch that has that already has contradictions. Okay, so if all the branches have contradictions, then we will say that the knowledge base is unsatisfiable. Okay, so these are the correct options, A, D and E. All branches need not be models for the knowledge base to be satisfiable, because if that is the case, then it will be a tautology. And it's not true that even if there are one branch that is that has a contradiction, then we can say that it is unsatisfiable, because there might be another branch that is a model, right, that does not have any contradiction and it ends up being true. So all the branches need to be closed for the knowledge base to be unsatisfiable. All the branches should be models for it to be a tautology, and at least one branch should be a model for the knowledge base to be satisfiable. Okay,
Sir, one question, sir.
yeah.
Sir, when we said that KB to be satisfiable and KB to be unsatisfiable.
Yeah. Oh, you mean to say when can we say that it's satisfiable and when it's not satisfiable?
Yes, sir.
Okay, so let me again try to explain this with an example. Let's go back to our simple example from mathematics. Okay, let's say we have x plus y equals to 4, or let's say something simpler, 2. Okay, so one particular assignment of values to x and y is 1 plus 1, right? Then there is 2 and 0, and then there is 0 and 2. All of these lead to this being true, right?
Yes, sir.
Now suppose another assignment is 3 and 1. This leads to this statement being false. So
Yes.
we cannot say that this particular assignment or this particular valuation is a model for the knowledge base, which is this. This is our knowledge base. Okay, whereas either of these assignments can be said to be models for the knowledge base. Okay, so when you solve the tabular method, let's say you did this extension, then you did some branching, then you did some extension, then you did further branching. Yeah, this branch has some more extensions and things like that. Okay, so this is what your whole tabular looks like. Okay, now out of these, let's say this particular branch has some contradiction, so you close this. Okay, this branch has some contradiction, so you close this. Okay, but it might be that this particular branch leads to the knowledge base being true. Okay, so whenever we adopt this particular branch, we will arrive at a truth value true for the knowledge base. Okay, or the or for all the statements in the knowledge base. Okay, so we can say that there is at least one assignment of the variables in the knowledge base that lead to the whole thing being true. Okay, so that essentially means satisfiable, right? But
Yes, sir.
if, let's say, let me remove all of these, if all of these branches lead to true, which means that no matter what assignment you do, no matter what valuation you do, the whole thing will always come out to be true. In that case, it is a tautology. Okay, if you have a situation where all the branches lead to contradictions, everything, then you say that there is no particular assignment of variables that leads to the model being true or the knowledge base being true. In that case, we will say that it is unsatisfiable.
Yeah.
Okay,
Yes, sir.
does that
Yes.
make things clearer?
Yes, sir. Thank
Okay,
you, sir.
that's great then. Okay, let's move on to question 7 then. So question 7 tells us that given the propositional logic language defined in the course, it is possible to have a knowledge base for which, and then we are given 4 options. So there are 4 possible situations that we might come across given a knowledge base, okay, and the definition of propositional logic that we have learned. So which of these options could be possible? So again, I'll let you go through the options for maybe a minute or so, and then we can discuss which of these could be true. Okay, I'll just go get some water. In the meantime, you think. Okay, I'll be back in a minute. Okay, so we have a couple of solutions, and I think most of you have uh, gotten it. So let's look at the options one by one. So let's look at option A first. Is it possible that there is only one linear branch in the entire tabulo? Every node has exactly one child.
No.
Okay.
No.
Think of a case where we have only and. Will there be any branching in that case? No, right? So again, coming back to the board, um, let's say our knowledge base has only and connected on and connected statements, right? So there will be no branching like this, right? Only expansion that will happen is in a linear fashion, right? So that could be possible, right? So option A could be true, or there could be a situation where there is only one linear branch in the entire tabulo. Every node has exactly one child. Okay.
So one is possible.
Yeah. So when you expand an and operator, you are so okay. Let me go back to the board. So basically, when you are doing A and B, and then A and B, you are adding. So this, if we expand this thing or we zoom into this thing, this is essentially represented like this. A and B derives A and B derives B. Okay, so there is linear expansion in the single direction, and then you have um, uh, A and B, which are single children of this one node that you have. So this in short form, or in, so that we don't have to repeat writing this whole thing again and again, we just write that A and B derives A and B separately. Okay, in that sense, option A works out. Does that make it clear?
Yes, sir.
Okay, or we could even have something like let's remove the and case. Let's say we have only unary connected operators. Let's say we have not A, B. That's it. That's all we have in the knowledge base. So we expanded only in the linear fashion. Okay, and there was only one child to each node, right? And there was no branching. So this can also be an example if the and example seems too complicated for now. Okay, so the bottom line is that option A is possible. Option B is also possible. There can be no linear extension. Every node has exactly two children, right? Which is when we have only or operators in the knowledge base, right? So at every expansion there will be a branching. It is also possible that there are no extensions at all, that there are no children, which also corresponds to the last example that we just discussed, right? If we are already given not A and B in the knowledge base, there is no need for any expansion for that matter. And then finally coming to option C, because we are given only binary and unary connectives, we cannot have three children in any case. So option C would be incorrect, and A, B and D would be the correct options. Okay. Okay, I guess this was clear.
Ritwis, in case of the example where you gave not A and B,
Yeah.
those are two examples. Statements, I would say, out of the knowledge base. But what are the childs out of it? If you're not able to expand them, then what are the childs?
There are no childs.
What are the, what,
Essentially, the
there is
child
no
of
children, right?
not A is not A itself. The child of B is B itself. The child basically
Okay.
means what we can derive from that particular node, right? And here we can derive only the same thing from that node.
So there is Oh, okay. So we can say that okay, there each node has exactly one child.
We can say that, I mean, depending on our interpretation. So actually, in practical consider from practical point of view, uh, adding this kind of an expansion to a tabular method is futile, because it doesn't add anything to the knowledge base, right? So we can just leave not a and b at that itself without explicitly saying that this could be done, is what I meant
So
to say.
that means, can we say that okay, these two nodes don't have child? And what was the option B then?
Option b was, there are, every node has exactly two children.
But in this case, we don't have children, right?
No, no. So option B corresponds to this. This whole thing is what option B corresponds to. Okay, there are no linear extensions, and every node has exactly two children. This will happen when we have only OR connectives. So let's say we have
Yeah, but
A
in
or
this
B.
case, it won't because we won't be able to expand it.
We will have two children, right? We will have
Yeah,
either
no,
A
but
or B.
in the previous case, not A and B.
Yeah, here there are no other possible extensions other than the futile extension. So yeah, here there will be no further expansions, and there are no children.
Yeah. Okay.
Okay. Anything else in this question before we move on?
I'm good. Thanks.
Okay, that's great then. So let's move on to question 8 now. Okay. So question 8 tells us that alpha, beta, gamma and delta are formulas over the set of propositions p, q and r. Okay. Let alpha and beta and gamma and naught of delta be a simplified notation for this conjunction. Okay. So recall that this is similar to adding the negation of the goal, which is let's say delta here, to the statements in the knowledge base. Okay. Now given the conjunction as input to the tabular method, which of the following can we show using just the tabular method? Okay, so there is a particular nuance to this question which I'll discuss when we discuss the solution, but I'll let you think on it for a while. Okay, so alpha, beta, gamma and delta are formulas. Okay, which means that alpha might be some combination of this p, q and r. Okay, so alpha might be p and q, beta might be not of r, gamma might be p implies r, or things like that. Okay, um, and then we have delta, and delta is something that we want to, delta is our goal, so we add the negation of the goal to the and connected facts in the knowledge base, and then we apply the tabular method. Now depending on whether the branches have contradictions or not, what are the different scenarios that we might encounter? Okay, suppose all of the branches of the tabular method are closed, which means that all branches have contradictions. In that case, what will we say? The conjunction is satisfiable, unsatisfiable. Which of those would we say? B. So some of you say that the conjunction is unsatisfiable in that case, which is true. Let's say one of the branches happens to have no contradictions. Okay, results in a model. Then can we say that the conjunction is satisfiable? That's right. That corresponds to option A, right? Which some of you just say. Now the trick is about tautology. Okay, so whenever we want to prove that something is a tautology using the tabular method, we have to we have to go one extra step beyond the tabular method. In order for us to prove that it is a tautology, we will first have to prove that the conjunction along with the negated goal is unsatisfiable. Okay, what we mean by something that being unsatisfiable is that there is no model for the facts in the knowledge base connected with an AND operator with the negative of the goal. Because there is no model for that particular conjunction, there is a model for the opposite of that, which is the non-negation of the goal connected to the conjunction that already existed, which means that it is a tautology. Okay, so basically what I mean to say is, in order for us to prove a tautology, we first have to prove using the tabular method that the conjunction itself is unsatisfiable, and then we do one extra step to say whether it is tautology or not. So just based on tabular method, we can only say whether the conjunction is satisfiable or unsatisfiable. Okay, so the correct options are A and B. Any doubts here?
Sir, you use the word one of the branch, something like that.
Yeah.
But we have all and connections. Then where is the question arising regarding branches? If we have R, then we can say about the branch.
No. So basically what I mean to say by this conjunction is, so alpha is not an atomic symbol over here. Alpha
It
is
can be
itself
something
a
else. Yeah,
formula. Yeah. So we will
Okay, sir.
expand alpha, beta, gamma and not of
Okay.
delta, and then follow the tabular method, and that will lead to some branches.
Okay. Here alpha, beta, gamma are not the atomic formula. It is
No,
just
no, no.
formula.
It's just formula. Okay, because it's written
Okay.
right. Alpha, beta, gamma be
Yes, sir.
formula
Yes, sir.
over P, Q, and R. So P, Q, and R are our atomic symbols.
Sir, right, sir. Sir, done.
Okay.
So can you explain the last step again from how to find tautology from this tabular method?
Sure. Let me just write it down. Maybe that will clarify it. So basically, let's say we have some alpha, beta, gamma in the knowledge base. Okay, these are statements given to us, and our goal is to prove that delta is delta has a model basically, right? Or delta is a tautology. What we will do is we will add the negation of the goal to the knowledge base. Okay, this essentially just represents our knowledge base, the facts given to us in the knowledge base. Okay, so we have alpha, beta, gamma and not of delta. We will expand each of these using tabular method. We will arrive at some particular tabular configuration. Okay, something like this maybe. Now we have to prove, in order for us to prove that this is a tautology, we have to prove that this particular thing is unsatisfiable. When this is unsatisfiable, only then we can say that because adding not of delta made it unsatisfiable, that means that adding delta would make it satisfiable and in fact a tautology, because it would be the exact opposite of what we got when we added not delta, right? So that is the extra step that we have to do when we go from unsatisfiable to tautology. Okay, and that operation happens other than the conjunction that we are dealing with, which is over here. So that is why the question says that we can only just, if we are just concerned with the conjunction itself, we can just say that whether the conjunction is satisfiable or unsatisfiable. Okay.
Thank you, sir.
Okay, that's great then. This is just a tricky way in which the question has been formulated. Again, not by me, but from in one of the previous years. And so I just thought it would be useful to include that, because this will just draw your attention to the fact that be careful on how the question is phrased and what exactly the question is asking. Okay. Okay, so there's a question in the chat box. When A is true, and C is false, then how D is true? Option D is not true, right? Option D is incorrect. Sorry about that. So option D tells us that, yeah, option D tells us that the conjunction is satisfiable but not a tautology. This can never happen, right? Because whenever something is tautology, which means that it is satisfiable on all branches. Something that is satisfiable may or may not be a tautology, but a tautology will always be satisfiable. So option D is incorrect just by the definition of, or what is given in the statement of T. Okay. Okay, then let's move on to the next question. In the tabular method, if no branch of the tabular being constructed for a formula is closed, it means that, again, be careful of the nuance that we just discussed. Here we say that no branch is closed, which means that there are no contradictions.
Alpha is a tautology.
Okay, first we'll say that it is satisfiable. Okay, tabular method will help us say that it is satisfiable, and then we will do one extra step to say that it is a tautology. Okay, so tabular method will only give us the result that it is satisfiable. Okay, does that make sense?
Sir, in that case, question number 8D, why we are not considering?
Question sorry about that.
Yeah, question 8D, same thing.
No. So question option D essentially here says that tabular method can help us say that the conjunction is satisfiable but not a tautology. Take this sentence together. Okay, what we mean by this particular option over here, that alpha is satisfiable, is that alpha is satisfiable, now it may or may not be a tautology. Okay, this is what the partial information is available to us. What option D tells us, that tabular method will help us prove that the conjunction is satisfiable but not a tautology. This can never be true, right? Because if something is a tautology, it has to be satisfiable. Okay, we basically, once we say that something is satisfiable, we cannot immediately say that it is a tautology. That's why option D is incorrect here. Does that help, Khalid?
No, it is not going in my mind. I'll think, sir, about that.
Okay, no worries. Just give it a thought, and if it's not clear, just let me know. We can discuss it again, maybe in the next live session itself.
Sir.
Okay. Also, please feel free to post this in the discussion forum as well. Maybe Bhaskaran sir has some good example up his sleeve where he can explain clearly using this tabular method. As of now, I don't have an example like that, but maybe I can also try finding that. But yeah, do post it in the discussion forum, and maybe that will also be helpful. Okay. Okay, then maybe this will also help you clarify to some extent this question 10. So question tells us that we have a graphical representation of the different propositional different subsets of propositional formula. Okay, so we have tautology, we have contradiction, we have contingency, satisfiable and unsatisfiable. Okay, so you can think of contingency and satisfiable as the same thing. Okay, they are basically the same thing that can be used interchangeably. We have to assign each of these colored regions over here, A, B, C and D, to these different subsets. Okay, so basically we have to say unsatisfiable corresponds to A, B, C or D. Okay, tautology corresponds to which one, A, B, C or D. Okay, we have to do a mapping in the Venn diagram. So which mapping do you think would be correct based on the definitions we just discussed? So the first demarcation that we can do is satisfiable and unsatisfiable formula, right? That's right. let's go ahead with the color red corresponding to unsatisfiable. Okay, so let's say that D is unsatisfiable. Okay, because once we say that a formula is unsatisfiable, or a set of propositional formula is unsatisfiable, we don't need to further divide it into further subsets. Whereas we see that A itself has two subsets, B and C. So let's assign A to satisfiable and D to unsatisfiable or contradiction. Okay, now within A we have two subsets, B and C. What do you think can those correspond to? That's right. So one of you says that C could be tautology, which basically means that within the set of propositional formulae that are satisfiable, there will be a smaller subset for which all the valuations are true, and that would make it a tautology, right? And everything else that is not a tautology, it's still satisfiable but just not a tautology, that will be the subset B. Okay, we could also have said that B is tautology and C is contingency, right? Just the other way around. We just went with C being satisfiable or tautology because it was colored green, but you could say the other way around as well. So the assignment will be something like this. A, the blue colored region is essentially what is satisfiable, everything that is satisfiable. D is everything that is unsatisfiable or everything that is a contradiction. Okay, now either of B or C could be a tautology, and depending on whether we assign B or C to be a tautology, the other one would be a contingency, which is again represented in this B/C or C/B over here. So does this kind of convey the relations between the different terms that we came across: tautology, contradiction, contingency, satisfiable and unsatisfiable? Okay.
So sorry to disturb you, sir.
Yeah.
Sir, actually, you had said in the last slide that something can be a tautology
Hmm.
only if it is unsatisfiable. We have to do an extra step. Am I right, sir?
Yeah.
So in that case, you have labeled D, the red one as D.
Hmm.
Tautology should come somewhere in within it, right, sir?
No, no. So there is a nuance to that. When I say that we have to prove that something is unsatisfiable, that is when we have added the negated goal to the knowledge base. Okay. So the total knowledge base with the negated goal is unsatisfiable, and that would belong in
Okay,
D.
okay, okay,
But
sir.
the
Okay.
knowledge base with just the goal, that would be belonging to C. If
Yes, sir. Yes,
yeah.
sir. Thank you, sir. Thank you.
Okay. Thanks for your question. Okay, then.
So same diagram, is it possible to represent what is given by professor, a semicircle, rectangle and a circle, and to tell satisfiable and tautology?
Let's look at that. This
Yeah,
one.
this one, sir. Sir,
Yeah, so it's somewhat similar. So here basically the square is the set of satisfiable formulas. Within that square there is some small subset T which is tautologies. Okay. Other than
sir.
the tautologies, basically the set S minus T, that is contingency, this region, and then everything else is unsatisfiable or contradiction. Is the same thing, just represented in a different way.
Sir.
Okay. But yeah, thanks for pointing that out, Khalid. Okay, let's move on to the next question then, which is question 11. So here we are given some atomic sentences, and it should be propositional representations. Okay, should not be proportional, so ignore that. So basically C represents Bob can make a call, D represents the battery is dead, H represents the Bob did charge the battery, Z represents the balance is 0, T represents Bob topped up the phone. Okay, so these are all the things represented by C, D, H, Z and T. Now we have to represent the statements given in 1, 2, 3, 4, 5 by some combination of these C, D, H, Z and T. okay, using some connectives. It might be unary connective like negation, it might be binary connective like or and, or even implication for that matter. So how can we represent Bob cannot make a call? Negation of C, that's right. Right, because C represents Bob can make a call, so negation of that would be Bob cannot make a call, right? Now let's look at the second statement, which is the balance is non-zero. This would be negation of Z, right? Because Z represents the balance is 0, so the opposite of that would be the balance is not 0, right? So second would be not of Z. Let's look at the third one. If Bob does not charge the battery, then it is dead. So let's break it down into two parts. The first part is Bob does not charge the battery, right? That can be represented by not of H, because H represents Bob did charge the battery. Yeah, is there a question? Okay, no worries. Yeah, so so we can
Not
represent.
much implication D.
Right, that's right. Thanks for the answer, Pankajini, and also Sridhar in the chat. So yeah, both of you are correct. So we can represent Bob does not charge the battery using not of H. Okay, and because we are given an if then kind of connective, we know that this can be represented with the help of an implication. So if not of H implies the battery is dead, which is basically D. So not of H implies D. Okay. Now let's look at option 4 or statement 4. If Bob tops up the phone, then the balance will be non-zero. So again, break it down into two parts and tell me how can we represent it?
D implication not Z.
That's right. So basically, Bob tops up the phone is represented by T, okay, and balance will be non-zero is represented by not of Z. So if T implies then not of Z, okay, so T implies not of Z. That is what option 4 represents. And finally, statement 4 represents. And finally, we have statement 5, which is if the balance is 0 or the battery is dead, then Bob cannot make a call. So how will we? So this you can break down into three parts. So the first part would be balance is 0. That we can represent using Z, right? Second part would be battery is dead. That we can represent using D. The balance is 0 or the battery is dead. That we can represent using Z or D, right? And Bob cannot make a call can be represented by not of C. And now because these are connected with the if then we can say that C,
Z.
Z or D together implies not of C. So these are the representations. I'll leave this on here for a few seconds so that you can convince yourselves. So any doubts in this question? Okay, if not then that's great. So this is the end of questions I had from week 3. So that's it from my side. If you would like to discuss anything specific, let me know before we close this session for today.
Since we have reached the end of the session and all the questions are done, can you once please explain like how we are applying the rules of inference like we did in the starting questions.
You mean the first few questions that we discussed?
Yes.
Okay, let me try to do that with one of the examples that we discussed. Okay, where is that? Yeah, so I'll just go over it. Okay, so we had all these different facts in the knowledge base. Okay, let me represent use a different color. We have P or not R. We have R and T. We have W implies S. We have P and S together imply Q, and T implies not of S. Okay, now we see which of these we can use to derive something new. We can firstly reframe or rephrase this first thing as not of R or P. Okay, it's the same thing, just the symbols have been swapped. So this is in the formulation of an implication, right? Not of R or P can be represented as R implies P. Okay, once we have this, we can use this in combination with this fact that we derived from R and T, right? So R and T, from this we can derive R as well as T. Okay,
We can derive R and T from this, like, because of the simplification rule.
yeah, that's right, because for R and T to be true, R has to be true as well as T has to be true. Okay,
So for solving these kind of questions, we will have to keep all the inference rules like in our mind.
yes, basically all the inference rules that we traditionally use on a day-to-day basis, I mean in this course, for that matter actually, which involves modus ponens, modus tollens, the simplifications and those kind of things. So I think the slide should have a list of those rules somewhere, right? Let me see if I can find that.
It is there. It is in the, yeah.
Something like this. Oh, this is for tabular, but you can this works for other cases as well, right? Basically, not of x gives not of x. X and y give x and y separately in a linear expansion. Basically, x or y gives two branches of x and y. Um, in the branching method that we were discussing, this is not really very helpful, but yeah, just to know in the tabular case of a tabular method, then not of x is x, and so on and so forth. Okay, I'm sure there will be some other lecture slide as well where you had a full list of these formulas, but you can explore that at your free time. Yeah, so we need to keep those formulas in mind and then apply those. So coming back to the problem that we had, we use this implication along with R to derive P. Okay, similarly we use T over here along with this implication to derive not of S. Okay, and then we use not of S along with this to derive not of W using modus tollens. Okay, and at this point we see that no further expansions are possible, no further derivations are possible, so we stop.
Yes, sir. Got it. Thank you.
Okay, anything else that you would like to discuss before we close the session, any of you?
Sir, week 3, 13th question, sir, and 12th, first 13, non-graded.
Okay, let me go to that.
Actually, similar to that, now we have actually addressed.
Question 13, you mean?
Yes, sir, 13.
Yes.
Answer is also is given. Last two are first one, alpha is unsatisfiable and alpha is a tautology.
Okay, so
it is just to reverse that what we are told. This is due to because minus negation effect.
okay, let me go through. So the questions are that let alpha be a formula over a set of propositions. After expanding not of alpha using the tabular method, if all the branches are closed, which means that not of alpha is unsatisfiable, right? And then alpha is a tautology. These two are correct?
Yes, sir.
Yeah, so that's basically a restatement of what we just discussed. That's right.
We are using the word tautology now very easily due to fact minus negation of alpha we are considering.
Yeah,
That is the reason.
yeah. So we can only say that negation of alpha is satisfiable or unsatisfiable, right? So that's what we are saying, that not of alpha is unsatisfiable. We cannot say that not of alpha is a tautology. We can say that alpha is a tautology because we are now doing away with the negation.
Sarah, okay.
Okay.
So now in the same just above that number 12, this also the question that we have done in the very beginning of this section.
Okay.
Can we address this question number 12 the way we have done it today's class?
So here basically instead of this we are given English statements, so we have to first frame this in terms of the propositional logic, something similar to what we did in the 11th question over here. Okay, so first we have to change
Sarah.
this from English statement, so this propositional logic representations, and once we have that, this
Sir.
will become similar to something like this that we just solved, and then we can solve it using any tabular method or this branching expansion that we just discussed.
Okay. Sarah, done.
Okay.
Sir, can you
Thank you, sir.
explain derived rules of inference again? Sir had
uh,
already explained in the lecture, but sir, I not understood.
which one, can you point me to that?
Sir, derived rules of inference.
This one.
Yes, sir.
Okay, let's see what is it. Any long proof can be added as a new rule of inference. For example, if you prove alpha implies gamma, given alpha implies beta and beta implies gamma, then you can add alpha implies beta, beta implies gamma, together proves that um, alpha implies gamma as a derived rule of inference to the original set. Yeah,
So
this
the
is the
third step, sir, I not understood the third step, sir. The
third
first
step.
one, second one, huh? The
Okay,
two
so
primary
basically,
reason.
yeah, so basically the first step is tells us that alpha implies beta. Second step tells
Yeah,
us that beta implies gamma,
yeah.
and then the third step tells us that beta implies gamma, tells us that alpha implies beta implies gamma. I think this concerns with the what was there at the initial slide, this Frege's rules,
Then
Frege's
one rule.
propositional calculus.
Hmm.
So I think we have to go through all of these then.
So
So
sir has applied here then one rule.
yeah,
Hmm.
so then one is
So
essentially,
what does it mean? I do not understood, sir.
okay, so given a set of axioms, which set of rules suffice to derive all the entailments. Okay, Frege showed that just one rule models ponens with the help with a set of connectives is complete, which is that using implication and negation we can derive everything else. Um, so then one rule basically tells us that alpha implies beta implies alpha. Okay, so maybe once we expand this, what will we have? We will have not of alpha or uh, beta implies alpha, which is not of alpha or not of beta or alpha or not,
Sir has told alpha is replaced by beta implication gamma and beta is replaced by alpha. What does it mean? Not understood, sir.
okay, even
Alpha
I
is
need
replaced
to,
by.
yeah, even I need to go through this once more. I need to revise what exactly was Frege's propositional calculus. So I would suggest that you post it on the discussion forum, okay, and ask Bhaskar and sir. I think I will need some more time to give a proper answer to this. Yeah.
Okay.
So maybe we can just remind me in the next live session, and I'll try to read up on this till that time. Does that
Okay,
sound good?
sir.
Okay. Anything other than that? Okay, that's great then. So then we can close the session for today. Thanks all for attending, and let's meet next week.